A brilliant physicist named Isaac Newton heard 350 years ago that you were finding forces a little tricky, so he came up with 3 simple rules that can be applied to any force you can imagine. Newton's first law is this: an object in motion stays in motion, and an object at rest stays at rest, unless acted on by a force. This means the velocity of any object anywhere in the universe is always constant unless a force acts upon it. In other words, in order to accelerate anything, you must apply a force. Newton's second and probably best law is this: if the forces are imbalanced, then the object will accelerate in the direction that the net or overall force is acting. There's an equation for this: F net equals ma. The third law states that every action has an equal and opposite reaction. Consider this: when you stand on the ground, the force of your body on the earth is matched by the force of the earth on you. You're pushing on each other. Remember these 3 laws, grasshopper, for they will serve you well. Let's have a quick practice with basic forces. According to the second law, we add forces that happen in the same or opposite direction. My car's broken and I'm pushing it all the way home. On the left is a force diagram. It shows all the forces acting on the car. Even top physicists draw these diagrams. They're super helpful. On the right is a diagram with our vectors. If I push my awesome car this way with a force of 40 newtons, and my friend helps me by pushing with 30 newtons, then the added force is 70 newtons in the same direction, right? This is the same as adding our vectors. Remember, vectors are added by joining them head to tail. But if my friend wants to be really annoying and pushes in the opposite direction, then his force becomes negative. This means that when we add the forces, we only have a net force of 10 newtons in the positive direction. Thanks for helping, not. Let's pick things up a bit. If I wasn't very good at pushing things, I might accidentally push my car diagonally downwards a bit, like this. We can think of this diagonal force as a bit of a forwards force plus a bit of a downwards force. We can use vectors to work out how much of my force is pushing the car in the forwards direction. Let's draw the vector for my diagonal force like this. My force is at a 35-degree angle to the horizontal. Time for some trigonometry. The diagonal is like a hypotenuse on a right-angle triangle. We can find the magnitude of the horizontal or adjacent side by using the cosine ratio. If I applied the same force of 40 newtons at a 35-degree angle, then 40 newtons times the cosine of 35 degrees equals 32.77 newtons. What we just did was find the horizontal component of the force. In this situation, it's the part of the force that's pushing the car forwards. Pretty painless, huh? We can find the vertical component also, using the sine ratio in the same way. 40 newtons times the sine of 35 degrees equals 22.94 newtons. That sucks, eh? We're pushing the car into the ground with a force of almost 23 newtons. What a waste of energy. Can you see how this would be helpful if we had to calculate the net force of 2 diagonal forces acting on an object? We'd do the same as we just did for each force. Use the sine and cosine ratios to break them up into horizontal and vertical components. Then we can add all the horizontal forces together and all the vertical forces together. Then using Pythagoras, we could find the final force like this. These are all simple forces, pushing objects in straight lines. But what about forces that make objects pivot or turn? There's this thing called torque. You've probably heard the word before, maybe in the context of cars. Remember this definition. Torque is the tendency of a force to turn or pivot an object about an axis. Let's put this into context. Ever notice how it's easier to push open a door near the handle than it is to push it by the hinges? Go try it if you don't believe me. The equation for torque is tau equals F times d, where F is the force applied straight on to the door and d is the distance from the hinges or axis in meters. We measure torque in Newton meters. If we increase the distance d from the hinges or rotational axis and keep the force F the same, we can see that bigger distances have bigger torque. And because we're good students and remembered the definition of torque, we know that bigger torque means a greater tendency for the force to pivot the door. Let's look at another handy concept. Forces is all about handy concepts. This one is called Hooke's law, and it's about springs. The equation is F equals negative kx. The law describes the force of a spring depending on how much it is stretched or compressed, and how springy the spring is. X is the distance that the spring is compressed or stretched. If we had the spring set up like this, we might say that stretching was in the positive x direction and compressing was in the negative direction. This minus sign means that the force of the spring is always opposite to the direction that it's stretched or squished in. That k is called the spring constant, and it's a number that just describes how springy the spring is. If we had a spring with spring constant k equals 0.4, and we stretched it by 2 centimeters, then we have a force of F equals negative 0.4 times 0.02 meters, which is equal to negative 0.008 newtons. So our force is in the negative direction, and really small. This is the force of the spring resisting the stretch. Use your imagination and you'll see that the application of this law is really massive. The last force is centripetal force. When an object travels in a circle, or as we call it, has circular motion, that object accelerates towards the center of the circle. These vectors show how the direction of velocity and acceleration changes in an object moving in a circle. Remember, when we have acceleration of a mass, we have a force. The force that accompanies this acceleration is the centripetal force. This centripetal acceleration is calculated as A equals v squared over r, where r is the radius of the circle. So the centripetal force is just F equals ma equals mv squared over r. Oddly enough, when we move in a circle, we feel like we're being pushed outwards. This is because our brains are being tricked. You might have heard of this outwards force before, centrifugal force, but be wary, it's not a real force. Remember to memorize Newton's 3 laws of motion. Use a force diagram to visualize the forces acting on an object. Use sine and cosine to find the vertical and horizontal components of a force vector. Torque is the tendency of a force to turn or pivot an object about its axis. Hooke's law describes the force a spring has when it's stretched or compressed. And objects in circular motion experience a centripetal force, which is directed towards the center of the circle.